Hi, I'm Chris FREY. I'm a professor of environmental engineering at North Carolina State University. My co-authors are at HKUST. And I'm going to talk about trends in Hong Kong ambient air pollutants and their implications for health effects. So the question we want to address here is, what is the net effect on human health of differing trends in ambient NO2 and ozone concentrations? And how are those trends affected by health effects of additional pollutants that are highly prevalent in Hong Kong? In Hong Kong, there's been recent work to develop a short-term added health risk model, which is the underlying basis of Hong Kong's Air Quality Health Index. And this model is based on daily hospital admissions. These are emergency admissions for respiratory disease or cardiovascular disease. The model is based on a 3-hour moving average concentration. So this is a slightly different averaging time than many of the US air quality standards. And it includes 4 criteria pollutants, including ozone, NO2, SO2, and PM10. So the important thing is that these models are derived from local data. And they are represented with the equation shown here, which is based on a linear exposure response relationship and the assumption of no threshold for adverse effect. As the basis for this project, we made a decision to focus on measurement rather than modeling. The advantage of measurement is that in Hong Kong there is a adequately long time series of high quality federal reference or federal equivalent method ambient air quality measurements at a relatively large number of stations that represent various locations throughout the Hong Kong region. Here we're using the monitoring network as of 2018. At that time, there were 16 stations, including 13 general and 3 roadside stations. And one of the general stations is Tap Mun, which is in the northeastern part of Hong Kong. And we use that as a background station because its ambient concentrations are not affected by local activity within Hong Kong. This graph illustrates the annual average ambient NO2 concentration versus year. In each year, we take the average of hourly data from each monitor. And then for the general monitors, we average for the 12 monitors other than the Tap Mun background station. And for the roadside, we average the 3 roadside monitors. And what we see for the background station is a very consistent background level of about 5 parts per billion NO2, perhaps with a slight decreasing trend over the recent years, but not really much fluctuation. And compared to that, we see slightly stronger trends, especially in the last 6 years of this data series at general stations for decreasing NO2 concentration. At the roadside stations, we saw a relatively flat trend up through about 2009, followed by a few years of increase, and then a plateau, and then several years of decrease. So one of the factors associated with the recent decrease in NO2 concentration has been the apparent success of a number of air pollution control measures enacted in Hong Kong over successive time periods, initially addressing replacement of very old diesel commercial vehicles, which are high NOx emitters, followed by increasingly stringent emission controls aimed at diesel commercial vehicles and franchise buses, as well as a program starting in 2013 to replace catalytic converters on the LPG taxi fleet that had failed. And these and other controls that are shown in the table are associated with the recent decreases in NO2 emissions. There are also programs aimed at other than motor vehicles, such as aimed at industrial and commercial sources and marine vessels, although those programs are aimed largely at other pollutants such as VOCs and SO2. This slide depicts the measured ambient ozone concentrations, again based on annual averages of hourly measurements in each year at each station. And the trend for the background site, the Tap Moon site, is there's some interannual variations and some slight hint of an increase, perhaps of a few ppb on average from 2000 to 2018. In looking at the general station data, there are periods of noticeable increases, and there is some interannual fluctuation in the trend, but the net trend appears to be a gradual increase in annual average ozone concentration. And likewise at the roadside station, there's also a gradual increase in annual average concentration. Of course, the annual average ozone concentrations at roadside are much lower than at the general stations because the roadside sites are very close to vehicle NOx emissions, which react with ozone to convert NO to NO2 and ozone to O2. So that's known as ozone titration. And so that's an expected effect at roadside to have much lower ozone than at the general stations. This is an analysis of data from the general stations that have been background corrected to look at the incremental change in ozone concentration from one year to the next versus the incremental change in NO2 concentration from one year to the next. And this is done using an orthogonal distance regression method that accounts for errors in both the x and y axis. The result here is a statistically significant negative slope, and the confidence interval on that slope is indicated, that illustrates that, as we expect, ozone concentration tends to increase as NO2 concentration decreases, or vice versa. And this trend is consistent with numerous other studies that are listed here on the slide. Likewise, we look at the sensitivity of the interannual difference in ozone concentration versus the interannual difference in NO2 concentration at the roadside sites. And here the strength of the statistical result is a little bit stronger, but it's also qualitatively similar in showing a negative sensitivity of ozone per interannual change in NO2. And so here again, we see an increase in ozone as NO2 decreases. And the ratio is a little different because the NO2 concentrations at the roadside stations are typically higher. This slide is a little different than the other slides in that this is no longer about concentration, but this is about the added health risk. And so this is based on every hour calculating the 3-hour rolling average of both NO2 and ozone concentration, and then for NO2 calculating the added health risk, and for ozone calculating the added health risk and summing those, and then repeating that for every hour. And then the annual averages are based on the averages of all the rolling 3-hour averages within that year. So when we look at, and these are background corrected, so it subtracts the added health risk from the background site. So what we see at the general site or the general stations is that there's not really a discernible trend, and there's no significant, no statistically significant trend in the general stations on average over all of the stations. But for the roadside stations, there is a significant decrease of 0.2 percentage points of added risk per year. And what we can interpret from both of these results is that the general stations, although ozone concentrations and ozone added risk has been increasing, NO2 concentrations and NO2 added risk has been decreasing, and these two compensate for each other to essentially no net change. At the roadside station, the reduction in added health risk from NO2 is a larger effect than the increase in added health risk from ozone. And so there's a net reduction in added risk at the roadside sites. In terms of implications for human exposure, people don't live either at the general stations or at roadside stations, but they do spend time in locations that are represented sometimes by general stations and sometimes by roadside stations. And so an implication here is that if you consider the movement of people throughout their day to different locations, the combination of these two is likely to result in a net decrease in health risk for a typical person. This slide adds two more pollutants, SO2 and PM10. And what this shows is for the general stations, when we include the added health risk from these two additional pollutants, then the overall health risk at the general station decreases significantly, although it's a small change. It's a change of 0.2% per year of a decrease. Whereas at the roadside stations, there's a significant decrease of 0.26 percentage points per year compared to the 0.22 percentage points per year when we only look at NO2 and ozone. So the bottom line is there is an enhanced reduction in health risk associated with considering these additional two pollutants as a mixture of air pollutants that poses risk. So with that health background on fine particulate matter, if we look at the trend in fine particulate matter concentrations in Hong Kong, we see at the purple background Tap Mun site and all other sites really, PM 2.5 was increasing up until about 2004. And with some interannual fluctuations, there's been a more or less steady decrease in fine particle concentrations through 2018. And so, I mean, this is a tremendous credit to a lot of work that's been taking place, and not just in Hong Kong, but in the Greater Bay Area to reduce ambient concentrations of fine particulate matter. The slightly higher fine particle concentrations in Hong Kong compared to background are indicative of the incremental additional ambient concentration from local emissions within Hong Kong. And but the general temporal trends, whether they're at the general sites or the ambient trends at the roadside sites, have roughly similar interannual trends. And you know, as is well known, fine particles are often don't have as much spatial variability as some other more short-lived pollutants, and that explains why these trends are so similar at the different spatial scale of background versus local, and at the different types of sites. So our key findings and conclusions are that locally adopted emission controls in Hong Kong have been effective at reducing ambient NO2 concentration. However, ambient ozone concentration has been increasing. However, the net additive risk from both NO2 and ozone has either remained approximately constant at general stations or decreased at roadside stations. Ambient concentrations of SO2, fine particles, and PM10 have been decreasing. The net additive risk from multiple pollutants has a slightly stronger downward trend than that only from NO2 and ozone, and this is for short-term health effects. Thus, emission controls aimed at SO2, NO2, and fine particles and PM10 have led to health risk reduction. However, the annual NO2 and fine particle concentrations are higher than WHO guidelines and merit further reduction. And of course, the long-term health risk from fine particles is an important component of looking at the overall effect of air pollution on human health. In terms of options to reduce ambient ozone concentrations, in the short term, VOC control should be a key focus. With continuing reduction in NO2 concentration, there may likely come a time where further NO2 reductions could lead to reductions in ozone, but given the nonlinearity in the chemistry, VOC control is likely to be more effective for now until deeper reductions are achieved in NO2 concentrations. So thank you for your kind attention. If you have any questions, you're welcome to contact either myself or my colleague, Dr. Alexis Lau, and we'll be happy to answer your questions. Thank you.